There was one question just about an issue that came up in last week's exercise about kind of inconsistent behavior of the output in the notebooks. Why is this slowing down Firefox? I don't want to deal with this problem. Yeah, so the issue was basically about getting different output running the notebooks for one of the exercises a few times versus running it once. And one thing that I was just going to suggest to people, if you see something like that, if you're getting kind of weird output that you don't really understand why you get different output when you run the notebook one time or another, you can always, in your exercise notebook, go up to kernel, and you can use the option to restart the kernel and either run all cells, which is maybe a good thing to do when you're finished with the exercise to make sure that that the output that you get is from running all of the cells in the notebook one after another. Sometimes if you've been editing things and you run the same cell several times over, you'll get different output. So I would say that, maybe before you're totally finished with the exercise, it's not a bad idea to do this restart kernel and run all cells to make sure that everything does actually work the way you expect it to. But if you're debugging something where you're getting weird output, you can also use the option to restart the kernel and run up to a selected cell. That way you can figure out, like, okay, things are all good until this cell, and then if you do the same option with restarting and running up to the selected cell with maybe the cell below, and you get different output than you expect, then you have some idea of how to isolate the problem that you're having. So one of the challenges with the Jupyter notebooks is the fact that because you can run the cells out of order, you can end up sometimes in situations where the output you get is seemingly inconsistent depending on the situation you're working with. So just be aware that these options to restart the kernel and run either all the cells or run up to a selected cell are good ways to test out and make sure everything is working as you expect. Effectively, our automated grading system does this restart kernel and run all cells thing when it checks to see whether you've done the exercise and gotten the correct solutions. So that's not a bad thing yourself to do, to make sure that you pass all the tests in the exercise by doing this before you submit your finished version. So so that's that. I think I need to find my way back down to where we were, which is perhaps here, and I don't know. I hope that I can continue with the notebook that I have. I may have to do this restart and run up the selected cells myself. But yeah, you were asked as our last thing before the break or during the break to do this rename or conversion option rather, to apply a function to several different columns at once and to store those columns as temp C, min C, and max C in our data frame. This is actually surprisingly easy to do. Whoops. If I stay in the notebook. I'm going to do this by making a list in here of cell names that I want to, or column names I want to use. So temp C, for example, and then min C and max C. These are the column names I want to use when I apply my function. And the way that I'm going to get those values to fill in is by doing data.apply, data, and then my, again, list of columns I want to apply this to. So it's going to be temp underscore F, min, it'd be great if I could type, and max. And then I'm going to dot apply to those columns the far to Celsius function. So kind of a long line here, but basically on the left side, what I have is my name in the data frame and then the three columns that I'm going to fill in. And they are listed in a Python list because it's expected that only one value here is given to the reference to which columns to use. So you have the square brackets, but then inside there you have this Python list with the names of the columns. Similarly, then I have the names of the columns I want to convert, and then dot apply, and then the name of the function to use, which will then convert the values in the temp F, min, and max columns to Celsius from Fahrenheit and store them as temp C, min C, and max C in the data frame. And if I'm lucky, yeah, it looks like I can run that and it works just fine. I could also maybe do data.head after this just to see the output. And I can see I have the temp C column like we did before, but now I have min C and max C as well. So it's possible to do data.apply with FAR to Celsius and do this to all the columns, but of course it doesn't make any sense to convert dates from Fahrenheit to Celsius, so that's why we select the columns we're going to use. And it's also possible, for example, to just pass in a single column to a function, but if you're going to be converting more than one, the dot apply approach is a little bit more, well, it's just a better way to go. So at this point, if we take a look at our data frame, we have here in the first 10 rows, I can get that by doing data.head with the number 10, the following values. So we can see that we have our date as the time column, we have temp F, we have min and max temperatures. I think all of that is pretty much the expected output. And now we're ready to move on to our next step. There's a little note here just in case you're curious about using iterows or dot apply. Iterows is a lot slower, so we show you how to do it just because it's kind of like using a for loop, something you've already seen, but dot apply is definitely more efficient. All right, so we're going to start down the path now to aggregating our data, and we're going to start that by dealing with how to parse our date values. So how to take from the dates that we have and extract things like what year and what month are we dealing with from the data. So if we look in the time column, for example, and we just maybe do .head 10 here. If we take a look in the time column at the first 10 values, you can see them listed here. And, excuse me. And we could look at the time here to start to see where our dates begin. We could also do data time dot tail, and let's look at the last 10 values we have in our time column to see when the last dates are in our data file. So we can see this goes up until, if we're looking at this in terms of the year, up to 2019, there's the month of October, which is the 10 that comes after that. The day is the 1st of October, and then the time is at 11:50 p.m. or 23:50 is the hour and minute of this observation. So we have those values, and we know that they are stored as integer values, so we don't even need to run this cell under here because we can see already that this is the data type int 64. We could run data.dtypes if we wanted to, which would also tell us that time is in the format of a 64-bit integer. So if we want to start to deal with things like extracting just the year from this, our first step is actually to convert these number values that are used for the date into a character string, because that's going to allow us to then select a certain number of characters to find things like what month or what year it is. So if we take, for example, our data frame and make a new column in here called time_str, we can take our time column that we have already, which is data time, and use the as type, we used this last week, to convert from the integer values that we have now to be a character string by doing as type str. So that's just going to convert the number values into being character strings in a new column called time str. So if we run that, we're going to get a new column in our data frame that would be called time str, and this character string has some useful properties about it because we can do things called slicing of character strings. I think we may have hinted at this in some other examples earlier, but we'll see how that works exactly right now in a demonstration like this. So let's imagine we have a date, and we know that our date str, our time str column contains character string values that represent the date. So if we took the last day that we have, it's 2019, 10/01, and then 2350, or you can copy and paste the text that's right here. That's the date of our last observation in the data file we're working with. If we want to get, for example, the date, just the year and the month from this, we can take a string slice that says, from this character string called date, go from character in position 0, so that's the first character in the string, up to, but not including, the character in position 6, or the index 6. So you can see that this is going to go 0, 1, 2, 3, 4, 5. So it should get us these characters. So this is kind of like using a selection in a Python list where you could select out certain range of values. You can do the same thing in a character string. It actually works a lot like a Python list. So if I run this, what I get from here is 2019, 10. So I'm getting the first 4 characters of the year, and then the next 2 after that are the month of that year. So the reason for doing this is this obviously makes it sort of easy in a way to pick out just, for instance, a given year, or a given year and the month of that year by selecting either the first 4 or the first 6 characters from this time value that we have when it's in the form of a string. So if we take the same idea and we apply that to our data frame, we could make a new column here called data. Let's call it year, what did I call it here? Year month. Where our data year month character value is going to be using our data time str. So that's the date converted from a number value to be a character string. And actually, before we do that, I'll add a cell here just to remind us. Data.head, so you can see all of our columns here. You don't need to type the data.head thing in here. I don't need to see my Twitter crap. But you can see here we have this time str column. It has exactly the same values in terms of the numbers that are in here with our date column that we already had. But for example, if I did data.d types, to check what the data format is, it comes back as object, which is the data type that's used to represent a character string in a data frame. So our time str is character string values now. Okay, so let's get back to slicing this. We're going to make a new column called year month, and we're going to start from our time str value, and we're going to use the built-in methods that are available in a Pandas data frame, because we can't exactly do the same thing that we did for just a single character string, but we'll do str.slice, and then we can say start equals 0, stop equals 6. So this is very much like the example that we just looked at above. And in fact, let me just cut these cells so that we can actually see the example we looked at above. So we had the date, and we selected characters 0 through 6 from this date to get 2019, 10. We're doing basically the same operation here, but we're using this .str.slice, which is the way you do it in a Pandas data frame, starting at 0 and stopping at 6. And if we run this, we can take a look here at our data frame. You'd see that it's going to print out data.head. And if we scroll over to the side, we now have this new column called year month. And you can see, for example, for the first observation, it's 1906-01, 1906-01, and it continues on like that because, of course, all of the first 5 rows are all observations from the same year and the same month, so they have exactly the same characters that are there. That's a useful thing because now we can take all of the things, all of the observations we have that have the same year and same month and group them together and do things with them, and that's kind of what we're going to do in just a moment. But before we do that, I think maybe I'll skip the check your understanding part of this and just kind of walk you through doing it. It's something useful to do. This is basically just an opportunity to kind of do the same thing that we just did, but we're going to do it with just getting the month. And I'll just show you how to do this because I want to make sure that we don't completely run out of time, because some of the things toward the end of the lesson are still useful for today's or this week's exercise. But if we did the same thing that we wanted to do before, we made year month before, but we could just make a column called month by making data and then month equals data, and then we have to use here time underscore str, that's our date as a character string, and then .str.slice. And in this case, our start is going to be equal to 4, and our stop will be the same 6 that we had before. So remember that the year is going to be the first 4 values, so that would be then index 0, 1, 2, and 3. The month is then going to start at index 4 and 5, and because the stop value doesn't include index 6, that's going to give us just the 2 characters that are in position 4 and 5 in the character string for each month. And if we run that, we'll have a column for months. And if we just took a look at data, let's maybe look at month and then year month. Or we could do it in the opposite order, it doesn't matter. But if we take a look at just these 2 columns out of our data frame, you can see here the month 01 corresponds to 1906-01, for example. So that's the way in which we could, for instance, isolate just the month from the dates that we have. So every case here for the month, if it has the same value like 01, it would be for January, but it wouldn't know which year. It would be for all Januaries. In the lesson, there's also some things here talking about date times or date time approach to dealing with dates in Pandas. It's actually really powerful and useful, but it's also a little bit more complicated. So we're not going to go through this in the lesson in any detail. But what I will show you, for example, is that if we wanted to create a column that is called date, and we wanted to actually store our date values in a format that's called a date time object, we can run the cell that's here and then run the cell underneath it to check the first 5 rows after this operates. Date time objects are effectively a way in which something like a string value, like 2019, 10, 01, whatever, can be converted to a sort of data format that is actually recognized as a date and has methods that can be used to calculate things about the date. So for instance, there are some operations that are challenging to do, like when you're plotting, for example. If you were to plot using the numerical representation we have of the dates, there would be jumps between different months because you would have something like 1906-01 and then some day, so it'd be like 1906-01-01, 1906-01-02 for the next day, and so on. But then when you get to the end of the month, there's 31 days in January, so it'd be 1906-01-31. The first day of the next month would be 1906-02, 01. So if you were to do a plot in terms of time, you'd have these jumps in there every time you encounter a new month. And the date time sort of objects allow you to actually recognize that, like, no, it's not like there's a whole bunch of missing days between the 31st of February or 31st of January and the 1st of February, but instead it's just the start of a new month. So if we make this new column called date, you can see the format of the output you get here is a little bit different looking than what we saw before. You can see that the 1906 is represented here, and then there's a dash between the year and the month, and then the day that corresponds after that. And you can also see that the time of day is now represented in a format that's maybe a little bit more like what we are used to looking at for clock times. You can also see, for example, that this is a date time data type, so it's a different data type than we have used previously. I don't want to distract you too much further with that, but if you're interested, you can go to the course page and take a look at the materials that are there to learn a little bit more about date times. If you're really motivated, they are very interesting to work with once you figure out how they operate, but we're going to stick with the way that things are done here just for the sake of simplicity and just skip over the date time things for now. We had tried to introduce this a couple years ago, and it was like, I think, just one step too complicated to introduce date times for the majority of the students. So, okay, where are we at? Right now we have our data frame in which we have isolated the year and month into a new column called year month or something like that. And our next step is going to be now to do some grouping of our data, because once we have this year month column that will tell us all of the measurements we have that are from a given year and that month of the year, we can then very easily take all of those measurements together and calculate an average temperature for that month, for example. So we can run a couple cells here. We can see that we've got 757,983 rows of data. Our data frame looks like this, and perhaps most importantly for us in the steps that we have going forward is that we have this year month column that we can use to start combining all of the rows that have the same year and month together to be able to calculate a monthly average temperature. So yeah, that's basically what we're about to do. And we can start by using this approach called group by in Pandas. So we can, for instance, make a new variable here called grouped. That's going to be data.group by, and then we have here year month. So what this is going to do is it's going to take a look at all the data we have in our data frame that's called data, and if it has the same year and month value, it's going to put them together into this structure called a group. So I run that cell. It doesn't seem like anything has really happened here, but let's take a look at what our variable grouped contains in it. If we run this type command, we can see that it's a type that's called the data frame group by. It's part of Pandas. It's a data structure that comes from Pandas. And if we look at the length of it, we can see there are 601 groups. As it turns out, this 601 groups corresponds to the number of unique months of data that we have. So we have many years of data, and each year of data we have data from the 12 months. Combined, we have 601 months worth of data, and of course within those months there are many different observations or measurements that have been made during that month. So the grouping thing is kind of nice because now we have compiled things so that we have a way to look at a given month's data and do something with it. Just as a confirmation, if we were to look in the year-month column and look at the number of unique values we have there, that's what this nUnique function does, we also get back 601, which means that in the year-month column, we have 601 different months of data. So like 1906-01, 1906-02, 1906-03, and so on all the way up until 2019 10, which would be our last year-month combination. So we could look, for example, at all of the different group keys here. This produces quite a bit of output, so it was commented out for the purposes of making the course webpage, but if you run the cell, you'll see all of the different groups that are here. So we have one group that would correspond to 1906-01, another group to 1906-02. So again, you can see it's the year plus the month. And doesn't really tell us quite how this group thing works yet, but it tells us that we have a whole bunch of these year-month combinations, and now we can take a look at what one of them contains, which might sort of be the kind of aha moment where you sort of suddenly realize how this all works. So let's start by specifying a month. Let's say that the month equals, and we'll say 2019-08 as suggested above here, August of 2019. Then what we can do is we could say group 1, we could call this whatever we want, but we'll just call it group 1 equals, and we could take from our grouped structure, we can get the group that corresponds to the month we defined here. So when we looked at all of the different key values here, this is just telling us all the times that we have data available. Each one of these keys, for example here, is 2019-08, can be used to find all of the rows from our data frame that have 2019-08 as the year-month value. So we can run the cell here. That this get group will allow us to sort of take a look at just the values we have there. And if we take a look in group 1, just type that in and run the cell, you can see here that the time column we have starts with 2019-08, 01 at midnight. So this is the first day in our data set that corresponds to the year 2019 and the month of August. If we scroll down to the bottom, we can see that the last observation we have is from the year 2019, month of August, on the 31st of August at 23:50, so 11:50 p.m. And the reason that all of these, I think we have now here 2,220 rows of data, that would be all of the values that are from the month of August in 2019. And the reason that we see that is because they all have the same value here in the column called year month. So that's how this grouping is working, is it's taking everything that has the same value for the year and month, or so the year month column, and if it has the same thing, it gets put in a group together. And that's essentially what this group by operation does. It just takes things from your data frame and says, okay, if you've got the same year month value, then you're part of one group. And in the end, of course, you end up with these 601 different groups because that's how many different unique year month values we have. Does that make sense? So I know it's a little bit complicated, but I think the basic idea hopefully is making some sense. And if we look, for example, at the type of the data we're dealing with, like if we just take our group 1 that we just printed out to the screen, we can see actually that our group 1 itself is a data frame. So this group by feature in Pandas creates a data frame for each one of the unique values we have for the year and month. And what that means is that if group 1 is a data frame, we can do anything that we can do to a data frame with our group 1 values, which is kind of nice. So we can do things like calculate the mean or the standard deviation or any of the other operations we would do to a data frame very easily. All right, so now we're going to do that. We're going to calculate the mean value for 1 month for the column dir, speed, gust, temp f, and temp c. So we'll do all of those columns at the same time. We're going to put it in this format just where we create a list of the columns first, just because it's easier to read when we do this. But we could say, for instance, that mean values equals group 1 dot, group 1, and then we'll put in mean underscore calls. So this will be the number of like the sort of different columns that we want to use, dot mean. So this will then take from our group 1 these columns and calculate the mean value, store that in a data frame called mean values, or I guess it's actually a Pandas series called mean values. And if we print that out to the screen, we can just type in mean values here to see what we get. We should have one number for each one of these columns. That would be the average, direction, speed, gust, temperature in Fahrenheit, and temperature in Celsius for that column. And yes, you can see, for example, here that in the month of August in 2019, the average temperature was 15.8 or 15.9 degrees Celsius, or about 60.6 degrees Fahrenheit. And the average wind direction, for instance, was 320 degrees for an azimuth. Okay, so now we know how to group things together. We know how, once we have a group, to calculate something like a mean value, and we're just like one or two steps from being able to do this for our whole data frame, to calculate an average temperature for every month in the 757,000 lines of data that we're working with. To do that, we're going to use a for loop. And the for loop in this case is going to go through each one of the groups and do this operation that we've just been discussing. So what we can do, for example, here is we can say for key comma group in grouped. So again, like with iter rows, when we loop over this group by object, we're going to get both a key that would refer to, for instance, the year and month we're working with, and then the actual data for that year and month that we're going to work with. And then in this case, we'll print out what the key is, and we'll print out the first rows of data from the group by doing group.head. So this is going to give us a data frame then, like we just saw. And of course, the break will then break things after doing that. So in our for loop, we can see that our key in this case for the first value in our grouped structure is 190601. It makes sense. That's the first data that we have in our data file. And if we look at group.head, the first 5 rows of data from this are, in fact, the first 5 rows of data we have in our data frame that we're working with. And so you can see, for example, all of the different columns that we have available to us in our data frame. So effectively what you see is that the key contains this year and month data in it, and we're just going to loop through each one of these different keys and do some calculations. So here we found a way to loop through the different groups that we have, but we haven't calculated the mean temperature, which is what we're going to do down here below. So this is the kind of like culmination of this part of the lesson in a sense. So let's make a new empty data frame called monthly data. We're going to pd.data frame. Boy, all right, there we go. This is going to be an empty data frame called monthly data, where we're going to store the monthly average temperatures for each year and month of data that we have. This is very close to what you're going to do in the exercise for this week, so hopefully that's helpful to see this here. Here are the columns, just like we used before, that we are going to calculate the mean values for. So wind direction, speed, gust, temp F, and temp C. We're going to iterate over the groups, which is basically what we just did using a for loop. So we had for key, comma, group, in grouped. We're going to calculate the mean value for whatever the group is. So for example, group, we'll call this mean values. Mean values equals group and then mean calls dot mean. So we just did this as well a moment ago. And I guess I just lowered my chair, but that's fine. So when we go through here, in looping through these groups, the group will be the data frame that corresponds to 1 month of data. And it's going to have, something like 2,000 rows in it, maybe. So our group, then we're going to take just this selection of columns out of the data frame for that month, and then calculate a mean value for all of those columns. Then we're going to, in our mean values data frame, the one that we created, or sorry, this is a mean values, I think it's going to be actually a series, but we're going to add our key in here to say that we have a value here for year, month, and that's going to be equal to key. Because when we loop through this, the keys that we have are these values of year, month that are the same for each one of the unique combinations of month and year that we have. Then we're going to take our mean values series, which is basically, because it's just a single column of values, it's a Pandas series, and we're going to convert that to a data frame because we want to be able to add each one of these things as like a row to this monthly data frame. So we're going to do this, which is to say that our row is going to be equal to mean values, which has all the mean temperatures as well as the year and month that they correspond to. And then we're going to do .to_frame, which will convert a Pandas series to a data frame. And then .transpose, which will take it from being a sort of column orientation to being a row. So it just kind of flips it 90 degrees. This used to be a little bit easier to do with older versions of Pandas, but yeah, this is how we have to do things now, this to_frame .transpose combination. So the reason for that is that what we're going to do then is take monthly data and say it's equal to pd.concat, which is it's short for concatenate. So basically it's kind of like append, but it's merging together two data frames. And what we're going to merge together in this case in a Python list is monthly data and row. Because row is a data frame itself, we're just going to merge together the empty monthly data we have with this one row, which basically just adds a row to the data frame. And then each time through the loop, we add another row to the data frame using this pd.concat approach. There is another way to do this. It's in chapter 3 of this Python for Geographic Data Analysis textbook that we're working on. It's a little bit more efficient, but it's also slightly more complicated. So I tried to just stick with this because it's the sort of simplest thing that we have. The only other thing we need to do here is to say that we should ignore the index. And that's because essentially every time we add a new row, we just want to start with an index of 0. We don't want to worry about what the index values were before in the rows that we had earlier. All right, so before we do this, just a quick review. We're creating an empty data frame called monthly data. There's nothing in it to begin with. We then are going to loop through each one of the groups we have in our groups that we created from our data frame that we began with, where each group would correspond to 1 year and month of values. So it's going to be a whole list of the measurements that correspond to whatever month we're looking at. We'll calculate the mean value for the different columns that we want for that month. We're going to then add to our Pandas series the key itself, which tells us what year and month this average data has been calculated for. Then we take the mean values series, make it into a data frame, and add it to this empty monthly data frame. And then each time through the for loop, we'll add a new row that corresponds to the average values of these columns for whatever the month may be. Does that make some sense? It doesn't need to be crystal clear right now. I understand this is a little bit complicated, and we've already been going for quite a bit of time. So you'll have the opportunity to work with this in the exercise. But the point is, this is the way in which we are going to condense things from multiple observations per day down to monthly averages. So let's run this thing. And you'll see it takes maybe a second or two to run, but it's fairly quick. And well, what do we have? If we print out our monthly data frame at this point, you can see that we have here columns called dir, speed, gust, temp F, temp C, and then a year and month. So ultimately, if what we want to look at is what the average temperatures are for the months, we have that now because we have, for instance, in the month of January of 1906, the average temperature in C for this Tampere Pirkkala station is about minus 3.6 degrees. And then you can follow through for the other months and similarly see how these average temperatures for each month have been calculated. So we have succeeded in aggregating our data, condensing it down from these multiple observations per day to monthly averages. We could do this another way. If we wanted to simply do grouped dot mean, it's also possible to do that, which will then calculate the mean values for all of these groups at the same time, but there may be some stations where it doesn't make any sense, like or things that it may not make a lot of sense to calculate mean values for, but it's also possible to do the grouped dot mean approach as a fast way to get average values for each one of the groups. Okay, so we're got about 30 minutes left if I push you to the absolute limit here. We still haven't done the probably coolest thing about this whole lesson, which is to take a look at which months are the warmest Aprils based on the climate data that we have available. So we're going to do that here. There's not so much for you to type in. It's more that you can kind of refer back to this just to see how it's done. But we could, for example, create a data frame called Aprils that's going to be equal to the data from our data frame when data month is equal to, and I guess this has to be a character string, 0, 4. So this is going to extract from our data frame every row where the month value is equal to 0, 4. Just gives us like, we're only concerned with April, so let's take 1 month out of the 12 and make a smaller data frame from that. That's the idea here. So it's the key thing perhaps is inside here, the data month equals 0, 4. So that'll create our Aprils, and then this is just going to make a subset of the stations of things that we care about, which is temp F, temp C, year, month, and station number. We don't really care about anything else here. We don't need the wind speed stuff. So we're just going to drop out some rows, or some columns rather, of values we don't need. So we can drop those by running this cell here. And then like we did before, we can group by year and month. So we could say grouped in this case equals Aprils.groupBy. Group by, and like we had before, by equals year underscore month. We don't want to group by the month itself because then we lose track of what year we would be calculating the average temperature for. But if we use the year-month column, it would be 1906-04, 1907-04, 1908-04, each one of those having its own group. So we can do that. Then we can calculate the mean for each group, which we can do the quick way this time, which is just to say monthly mean equals grouped dot mean. So we created this new set of groups for the Aprils so that each year basically each year has its own group for the month of April, and then we calculate the average value for each one of those groups like this. And let's just take a look at what do we have in monthly mean at this point. Mean.average dot head. Okay, so I appreciate I might be going a little bit quickly here, and don't worry too much. This is mostly just to sort of demonstrate how we can do this calculation of which April is the warmest. But what you can see here is that 1906-04, we have average temperature of about 3.8 degrees. In 1907, it was slightly cooler. 1908, it was slightly cooler. 1909, it was actually average below freezing, and then quite a bit warmer in 1910. So we have all of these different years now, an average temperature for the month of April. Now, in order to figure out which one of the Aprils is the warmest, we basically need to now sort things so that they are descending from the column, in this case, being temp C. So if we take our monthly means, or monthly mean, and we say dot sort, that'll allow us to sort the values, or dot sort underscore values, I guess, in this case. And well, what are we going to sort by? We're going to say by temp C, because that's what we want to use for our sorting. Ascending equals false because we want it to go from warmest to coldest, not coldest to warmest. So ascending equals false. And then from this, let's just take the first 10 rows. So we'll add in here dot ted 10. We don't necessarily need to do that, but let's just take a look at the first 10 rows. So we're going to see the 10 warmest Aprils at the Tampere-Pirkala station by running this sort. And of course, like any well-designed demonstration, it would be disappointing if we didn't see that 2019 was the warmest April at this particular station. It's not true for all the stations, but of course we picked one where that would be true because it nicely fits the goal of the exercise, which was to take a look at the warmest Aprils with the idea that April of 2019 was the warmest on record. But you can see that it's not necessarily consistently the case. In fact, here you see that in 1990, so almost 30 years earlier, was the next warmest April, and then 1989. So it's not sort of always the case that this is very consistent, and you'll see different patterns at different stations. So that's basically the way in which we can do this. Then if we want to repeat the analysis with a larger data set, we have here already filled in a quite busy cell that you don't have to do anything to but run, but it basically goes through all the steps of what we've been doing in a single cell. If you run it, it will calculate the monthly mean values for the data file that we're working with, and you can see then some output printed to the screen showing the year and the month and the station's values and average temperatures and whatever, in this case sorted by the warmest temperature average for that month. And we can see, for example, that this applies to the station 29440, which is the one we've been working with in the exercise. If we want to do this for more than one data file at a time, we have to use a module we haven't used in Python yet called glob or glob. I don't know what the pronunciation is. I think it's glob. But what it allows you to do is find files in a directory that match a certain character string that you're looking for. So we can import it first just by running the cell here. And then if we want to find all the text files in our data directory that start with 0 and end with .txt, we can do that by saying that we'll make a file list that equals glob or globe.globe. Should look it up at some point how to actually say that. It's going to be a raw character string, so you have the R in the front of it, and then we're putting in the full file path, so it's going to be a bit of typing here. So it's a /home/jov yan/shared/data/l6/ And then we would have 0 star txt. So all this stuff at the beginning here, up to L6, is basically just telling us what directory to look in. Okay, /home, Javian, shared data L6. That's the directory where we're going to go looking for files. The last thing that's given here is basically what's going to help us to define which files we want to include in the set of files we want to find in our file list. And in this case, it's going to be any file that starts with the number 0, has anything in between 0, and then ends with the characters txt. So this will give us anything that starts with a 0, ends with txt. So if we go to the file browser for just a second here, go back to our shared directory data L6, you can see that all of our data files start with the number 0 and end in txt. But we also have these metadata files that end in txt. So we don't want to include those as like files we want to analyze, which is why we say that the file name we want would be anything in this directory that starts with a 0 and ends in txt, which will exclude then these 3 metadata files that we don't want to mess with. So that will create our file list. And if you run the cell after that, you can see, for example, that number of files in the file list is 15. And you can see the names of locations of all the files that Globe found in its search for files that met our characteristics. So they all start with this part of the file name and then have something in here and then end in txt. Okay, so if we took a look here for each one of these file paths in our file list to print them out to the screen, you can see basically all the data files we want to analyze. So we're almost ready to go here. The only difference between what's done, if I scroll back up to this cell that had a whole bunch of stuff in it, which is basically all the steps we've been doing to analyze our data, the only difference between what's done here and what we're about to do is that you can see when the file path is set here to read in our data file as FP. Earlier in the lesson, FP was the name of the single data file we're working with. Now, we're going to create a for loop that will go through each one of the files we have and create in the variable FP the reference to the file that we want to load. And so we have basically here a for loop that's for each one of our files going to assign the variable FP with the location of that file. Otherwise, we're doing everything the same as what was done in the cell above. It's just that FP changes each time, so we're going to do this now 15 times as we go through the list of files that we have. Going to run this cell, and you'll start seeing that there's output that gets written to the screen. So it tells us the station number, number of observations from that station, and then it shows us the warmest April on record from that station. I don't remember what these stations' IDs are. You'd have to look in the metadata to see which ones are which. But in this first case, we can see that 1937 was actually the warmest April on record at that station. Then we have 2011, 1989, which we had seen was a warm one elsewhere, 1921. So it's quite variable which stations have the warmest as 2019. Okay, well, there's the station we were working with Tampere-Pirkkala. 2019 is the warmest there. 2019 is warmest at the next station in the list. And as you scroll through, you'll see the month of April in 2019 as the warmest in many of the stations, but not all of them. But if you look for the stations where it's not the warmest, it's usually in the top 5 somewhere. So although it may not have been the warmest on record at individual stations, it's clearly quite warm month in general. And again, you'll look around, you'll see that it's top 4, top 2, and so on. So the output we have here then is from reading in, I guess, 15 different stations worth of data. Total number of lines of information that we've processed is quite significant. So there's about 200,000 lines. Here's one that's getting closer to 930,000. I don't know if we have any more that have more than 1 million lines of observations, but you can see that we're dealing with some fairly big data files, and the whole operation didn't take much time. It might have taken 30 seconds or maybe a minute to run through and analyze all of these data files. So, very long lesson today. Apologies about that, but I think this kind of gives you most of the tools that you need for the exercise for this week. And I'll take just a moment to kind of highlight a couple things, and then we'll take a quick look at the exercise itself. But are there any questions at this point before we go there? I feel like I'm taking all of your energy with this lesson today, so sorry about that. This is always a heavy lesson. It's also probably one of the more interesting ones in the sense that it really gives you an idea of what you can do with pandas. But it's a heavy one. Okay, so just a note on the course page, we won't go through these lesson materials, but there's stuff about dealing with errors that you can find there. I would encourage you to take a look and at least read through it, because it breaks down things like the kinds of error messages that you commonly get when something goes wrong in Python and how to read and interpret those error messages. So for example, here you can see an example of a syntax error, and that's the name of the error itself. Then you have some extra text that's trying to describe to you what that error means. You have the line where that error occurred, and then you have even an indication in the output of where Python thinks the error message might, or the error itself might be in the example here. So you'll see a few different kind of error types that are there. You can read through and learn a little bit more about index errors, name errors, indentation errors, and so on in the course page materials. We also have a good coding practice this week about using assertions. I would like to have had time to go through this because it can be quite helpful. But assertions are basically a way to sort of assure that a condition is met when you're running a program. So for example, if we had a function to convert wind speed from kilometers per hour to meters per second, we could use that conversion function to do that exact calculation. But we would see, for example, a wind speed of 9 kilometers an hour is 2.5 meters per second. That's nice. But because wind speed is a value that should always be 0 or greater than 0, there's no such thing as a negative speed when we're talking about magnitude of a velocity vector. That's not something that we get into. So we could put in this condition that says, okay, when someone uses this function, we will assert the condition is that the speed has to be equal to or greater than 0. So this goes through an example of if you put in a negative wind speed, you get an error message, basically this assertion error. And in fact, there's an example here where you can add the text to tell the user, for example, wind speed values must be positive or 0. So it's a way to kind of, when you build a function, to make sure that it's being used the right way. So that's what the good coding practice covers, is about assertions and how to use them. That might be something kind of also a bit interesting to consider. And then lastly, there's a couple examples about ways to debug your code, which are kind of just some general recommendations about, when you're testing things, to make sure that you use something where you know what the solution should be to make sure that your code does the right thing. If your code's crashing, like, don't read in 10 million lines of a data file. Just read in like the first 5 lines, and if it crashes, try to make it crash quickly so you can figure out what's wrong rather than waiting 5 minutes every time it has to read the data file or to do some kind of heavy processing. And then last thing is to, like, when you make changes, like we've been doing with GitHub, make small changes and then save your changes to GitHub so that if there's a problem, you can go back to when the code was working. If you fill in the entire exercise and commit one time, you'll have a huge number of changes in that commit, and you won't necessarily know what to do if something has gone wrong. So those are the other elements for today's lesson. I'm sorry we didn't have time to go through them, but at this point, it's probably good to just say a few words about exercise number 6. So about that, we have in exercise number 6 3 problems and 1 optional problem, so sort of similar to how things have gone for some of the earlier exercises. However, in this case, Problems 1 through 3 are all in the same notebook. So there's just one notebook that you'll be working with. We're going to again be dealing with climate data, in this case taken from the NOAA once again, and in a data format that is described here, where we have things like a station, elevation, latitude, longitude, date, precipitation, average temperature, max and min temperatures, and you can take a look at the data file if you want in the exercise page. What do you have to do? Well, in this case, we're going to explore an exercise about calculating weather anomalies. So back in the very first lesson, we saw these animations showing how temperature deviated with time for different parts of the world, and that's essentially what we're going to be calculating here, is how much warmer is a given year or cooler is a given year than the long-term average. So the first step is to read in the data file. You'll see an example of what the data file looks like. I don't know if this link is going to work. I guess it does, but it's 2 megabytes, so it takes a moment for it to load. But this is the file format that we're working with our data file. What's kind of tricky here is that our missing values are not indicated by stars, but indicated by -9999. So you have to figure out some way to handle that situation of reading in data with -9999 as the missing data value. So you'll read the data file in. You'll skip the second row because that's also, I failed to indicate that, but we have headers, but then we have this nasty thing that looks nice in terms of formatting the file, but is not something we want to read in as data, so you'll have another challenge to figure out how to skip over reading the second row, but to read the first and every row after that. Then, once you've read the data file in, you'll run a couple tests, do a few calculations, and basically just explore a little bit of the data that you're working with. Problem number 2 is about calculating monthly average temperatures. This should hopefully sound familiar after today's lesson. And that's essentially what you're going to be doing, is to be calculating monthly average temperatures for each year and month that you have in your data file. So you'll be making a new data frame. You're given the name for that. You'll have a column in there called temp Celsius that contains your temperature values in Celsius that are the monthly average for a given year and month. So this would be like the average temperature for January of 1906, and then the average temperature of February of 1906. And then you'll convert those values from Fahrenheit to Celsius, and that's going to be more or less what to do for problem 2. There's not a lot that looks like it's here, but you'll have one code cell that's pretty full of stuff. Then problem 3 is about calculating these temperature anomalies. So if you want to know how much warmer or colder a given month is than the long-term average, you have to calculate what the long-term average is. And in this case, what we're going to do is we're going to take the average temperature for a given month, like January, and say what was the average temperature of January from 1952 up to and including 1980. So we have something like 30-year period or so that we calculate a long-term average temperature. And we're going to create, in this case, a data frame called reference temps. So importantly, the thing that's different here is we're not calculating the average temperature of January 1952, January 1953, and so on, but rather the average temperature for January for every year between 1952 and 1980. So it should be a single value for that whole 30-year period that we're referred to, for example, January. So in the end, your reference temps data frame would have a given month and then a single value that would be the reference temperature for that month. Once we have that long-term average, we can then take the month of January of 1906 and say, okay, was it warmer or colder than this long-term average? And you can then see from that how much the temperature deviates from the average temperature for the reference period. So that's what you're going to be doing in part 3. That's probably one of the kind of more conceptually challenging parts of the exercise. But don't worry, there's some instructions that are given here that I would encourage you to kind of look through. And there's also some hints on the course page about things like we have to do a table join in this. We haven't shown you how to do that, but there's a description of how to do this in the hints on the course page. And there's also some kind of figure here to give you an indication of what the different data frames are that you should be ending up with when you're doing this problem. So it might feel a bit complicated, certainly when you're working through it. I think it's it's probably the most challenging exercise in the course. But it is doable, and I would say that the sort of advice I would have for you would be to take advantage of the resources you have available. Like if you can make it to the exercise help sessions on Thursday or Friday, please go to those. If you have questions, please ask on Slack or contact us for assistance. I think on some levels it's challenging, but I also think that in some ways it's also very rewarding when you get it to work. Like to see that you can do this kind of calculation, because it really is the kind of thing that's interesting to look at, to be able to look at temperature trends over time. I mean, we can certainly understand things about how the climate is changing locally and globally by being able to do this. So I think that's quite interesting. Problem number 4, if you're a glutton for punishment, is to do basically the same thing that you've done in problems 1 through 3, but for a different weather station. This time it's the Sodankylä Lokka station. And note that the ä is not here in the name because it's basically just the database that the data come from. Ä is not part of the alphabet in the US, so that's not a character that can be used in that database. So if you want, once you've finished problems 1 through 3, you can go and repeat the same kind of thing for problem 4 to get more practice and to also then be able to compare. I think this Sodankylä example, I don't know, is the other data maybe from, I don't remember where, is it from? It probably says somewhere. If we look at the data file, do we have a, it's got to be somewhere in southern Finland. I don't know if it's Helsinki area or not. Maybe somebody knows the latitude and longitude of where we are precisely enough to know what town that would be or city, but my guess is that it's somewhere. It's got to be southern Finland based on the latitude, but I just don't know where. Would make sense to be Helsinki area. And it probably says in the description here somewhere, but I'm just not seeing it at the moment. Anyway, that's the exercise for this week. Are there any questions? I hope you're not completely overwhelmed with the sort of task that's in front of you. It's not impossible. It's not easy, but it's something that I think you have the skills to do. Just please try to take advantage of the resources we have available. If you have any individual questions, you're welcome to come up and ask me or talk about things after we're done. But if there's nothing else urgent, I think that's it for today. And we'll see you in the exercise sessions or back here next week for our final lesson about data visualization.